Many thanks for having me at this fantastic workshop. And this was just a really great presentation that we saw on human-machine teaming. I really liked it a lot. I would have liked to ask a number of questions too. Maybe we can go back to this later. The presentation we just had was on the interaction between humans and computers or machines. In my talk, I want to focus more on the machine side, but you'll see at the very end that we'll come to a more human-machine teaming approach that might, in fact, be facilitated or even demanded to a certain extent by the law. Now, the core topic of my presentation will be one of the, I guess, core aspects of AI ethics, namely algorithmic discrimination. And what I'll present is joint work with Meike Zehlike, one of the two formidable chairs, coincidentally, of this workshop, and Emil Wiedemann, who is a mathematician at the University of Ulm. And I myself am a lawyer, and this kind of setup of the authors is also reflected in the outline of my talk. So at the very beginning, I'll very briefly say something about the law of algorithmic discrimination. Then we'll try to shift perspectives and look more at the technical side of algorithmic fairness tools that seek to reduce bias in automated decision-making systems. But we will see, so in this context, I will also present the core part of the novel approach, of the novel algorithm that we developed in our paper. And then in the third step, we'll see that there are significant normative and legal challenges still remaining for implementing algorithmic fairness tools. So with this agenda, let's quickly jump into the legal part to start with. And before looking at certain legal qualifications, we should perhaps ask the question whether this whole scenario of algorithmic discrimination is in fact a more theoretical challenge, or if it's something that we can see in reality too. And many of you will know that indeed there is a growing number of studies and reports that documents cases of algorithmic bias in AI systems. So for example, in 2018, Amazon had to discard its AI recruitment tool because it persistently discriminated against women. And similarly, more recently, researchers found that an AI tool that was used to manage the patient population in hospitals exhibits racial bias. Now, with these cases, in reality popping up, the question is, how does the law deal with this? And I can only give you a very, very brief overview of EU law in this respect. I've written a longer paper that's called Teaching Fairness to Artificial Intelligence that goes into this in more detail. We should perhaps start by noting in anti-discrimination law that the law does cover algorithmic decision-making. It's not the case that it doesn't apply anymore only because an algorithm is calling the shots. However, oftentimes the result of algorithmic discrimination will be somewhat a side effect, an unintended side effect of machine learning optimization. In fact, it's often not going to be intended by the deployers of these systems, and that is something you might ask, or you might think that might be difficult to capture in the law, but in fact there is a category, specifically indirect discrimination, that deals with this and that covers quite neatly such cases of unintended bias, because it obtains when we have an apparently neutral practice that puts protected groups at a specific disadvantage. So what you need to show is some statistically different treatment of the different protected groups, irrespective of the fact if this was intended or not by the decision maker. Now, note that under EU law and also under US law, discrimination is not prohibited per se. Rather, it can be justified if you have a legitimate aim and if the discriminatory practice is proportionate to that aim. That means that we will have to think about the aim of the decision maker, but also potentially, and that's what I would like to suggest here, potentially about the technical source of the bias that Meike has already hinted at in her introduction. Now, I would tend to think that there's a crucial difference between bias training on the one hand and cases where you have unequal ground truth on the other. If you have a case of bias training, say, for example, you have sampling bias where one group is overrepresented or underrepresented in the data, or you have historical bias in a data set, all the cases that Meike already mentioned. In these cases, I believe that it's going to be very difficult to justify the use of the model, because you have a model that does not correctly represent reality and that perpetuates bias, historical bias, particularly in social bias, which is something that anti-discrimination law is supposed to prevent. However, you might have cases where everything, goes quite all right in the ML pipeline, but in the end you have different results between the different groups, and that's because the targeted qualities are in reality differentially distributed between these different groups. For example, you might imagine that you want to predict some kind of accident risk if you want to hire a new driver, and in that case, since men could potentially in that area tend to engage in more risky behavior, it could be the case that the scores of the male candidates are more prone or show more risky, more risk profiles, or higher risk scores than those of the other genders. And in that case, there is CJU jurisprudence, so jurisprudence of the Court of Justice of the European Union, that suggests that if there's a real difference in reality between the groups, it's going to be much easier to justify that kind of tool or outcome. Just for the lawyers, obviously insurance is going to be totally different. The Testa-Shah ruling of the CJU enforces unisex tariffs here. Maybe if you're interested in this, we can take this up into the discussion. Now, we have cases that I said of indirect discrimination. We have possibilities of justification. So this seems to amount to a sort of flexible framework that covers quite neatly the cases we have. But the problem, mainly for victims, is that they need to differentiate between different sources of discrimination, biased training data, unequal ground truth, to gauge their litigation risk, the chances of success. And that is something that leads to a rampant enforcement problem in anti-discrimination law, because oftentimes victims will not have access to the data and the models. Now you could say, well, now we have the GDPR, maybe that can help, and in fact, yes, I suggested in this paper that I mentioned that we could use Article 15 GDPR. That's an article that gives you access rights to certain types of personal information, that we could use this tool of the GDPR to endow victims with the right to get information from the decision maker about the different statistical distributions of the scores between the different protected groups. However, this is only one proposal, and it's highly unclear what the CJU will make of this. So this leaves us with the result that law in general, I think EU law is quite able to capture different varieties and different cases of algorithmic bias, but we have a rampant enforcement problem. And that's why it is so attractive to look at algorithmic fairness. That means tools that seek to guarantee or to implement societal and legal values such as non-discrimination directly at the code level, at the level of the model itself, in order to prevent basically discrimination from happening ex ante. Now, when we talk about algorithmic fairness, the question, of course, is what do people mean when they talk about fairness? And in fact, there's an abundance of fairness definitions. Nina just hinted at that in her talk too. So there are over 20 concepts that are tossed around in the computer science literature, but they can be grouped effectively into two main categories. The first is individual fairness. So individual fairness obtains if you have two individuals with similar input data, so similar attributes, except for the protected attributes, and they are mapped by the algorithmic process onto similar output. And that harks back to an Aristotelian notion of treating likes alike. And interestingly, this is a concept that was taken up by the CJU in its definition of equality before the law. So individual fairness is highly relevant for the law. However, the second category, group fairness, is relevant too. Group fairness comprises a number of different fairness metrics, and one that is quite canonical in the literature is statistical parity. It's also called demographic parity, and it obtains if you have the same positive selection rate for each group. So basically, you have the same score distributions for each group. That is a concept that is not meritocratic like the Aristotelian one, but rather outcome egalitarian. And the importance in the legal context is that if you satisfy statistical parity, it's going to be very hard to find indirect discrimination. Remember that I said that for finding indirect discrimination, you need to show that groups are statistically treated in a different way. So if you have, statistical parity, they're treated statistically in the same way. Now, what can we do with these two different groups? It would be nice to have your cake and eat it too, meaning to satisfy these criteria simultaneously at the same time. But unfortunately, there is a certain trade-off that's necessary in many cases between more group fairness and more individual fairness. More precisely, if the base rates differ between the groups, so if the true score distributions between the groups are different, then enforcing more group fairness will usually lead to less individual fairness. And that's where we started in sort of the development of our model, in which we tried to bridge this divide by designing a model or an algorithm to continuously interpolate between different measures of individual and group fairness. So what we did is we take the different score distributions, raw score distributions of the different protected groups, and we calculate a barycenter, that is an intermediate distribution that is as close as possible to the different raw score distributions in the least square sense. And that's our target distribution. And then we introduce one parameter theta that shows, or that we can choose between 0 and 1, and that determines the degree to which we map these raw distributions onto our target distribution. And in fact, we can choose the parameter differently for different subgroups. And if we choose theta equaling 0, this means that individual differences between the groups as they show up in the raw scores are fully preserved, and a certain variety of individual fairness is then met. However, if we choose theta equaling 1, we fully match these different group distributions onto the barycenter, and hence completely fulfill group fairness, that is in the sense of statistical parity. And we can choose any intermediate goal to sort of trade off between these different concepts. And interestingly, we use a mathematical theory that's called optimal transport to minimize the information loss when in this mapping exercise from the raw score distributions to the fair score distributions. Now, how does this work in practice? Just to give you one real quick example, we validated this algorithm on the LSAT dataset. That's a dataset containing more than 20,000 data subjects and recording their law school admissions test scores. If you look at the descriptive statistics here, you see that two groups stand out. One is the blue group that performs significantly above average, and that's the white applicants. There is one other group, the red group, that performs significantly below average, and those are the black applicants. Now, if you believe that this corresponds to true differences, in aptitude, then you might as well leave theta equaling 0, and you just take these scores as baseline for your admissions decision. If, however, you believe that this difference is rather due to social, historical, and economic factors, then you might choose higher theta values approximating the group distributions. For example, for theta equaling 0.5, you get this, and theta equaling 1, you match them. And then you can use these new fair scores for your admissions decision. And I think there are very good reasons in the case of, for example, education and college admissions for using higher theta values. That works with our algorithm, but the big question, of course, is it even legal to do so? And what are the normative questions that lurk in the background? In the last minutes, I'll just dedicate some thoughts on these to these issues. First, some open normative questions. I believe that the strength of our model precisely is its flexibility. So we can adapt it, choosing different theta values to different decision-making situations where more of an individual or group fairness metric may be desired. But and that's actually important because in anti-discrimination law, for example, justification is highly context-specific. So we can match this kind of threshold, the theta threshold, to different legal thresholds or regulatory constraints that we see in different areas. However, this flexibility is also a curse to a certain extent because somebody has to take this decision. And the question is, who decides on what fairness metric to use, what theta value to use? So we could think about, decision makers, just letting them decide. That's a first approximation. But in some cases, there will be parliament potentially in the background who could intervene and say that in certain areas, we want almost full group fairness, such as, for example, education admissions. And there could be, of course, the courts who take a decisive role if one of these questions actually comes to the courts. There is a second open question, and that is substantially, what theta value should we choose? To what extent should we enforce group fairness? And that is something, the answer to this question is going to depend a lot on the normative theory that we embrace. For example, if we choose a more, say, a more capabilitarian theory of justice, then we might say that, in fact, basic capabilities, basic amenities, perhaps such as housing or education, they should be allocated with higher theta values with greater degrees of group fairness, whilst in other areas you might have more meritocratic systems that apply. But obviously, if you choose a different normative theory, you'll have different answers. And that's something that's certainly up for greater societal debate. And third, finally, we've seen in Meike's intro also that a lot of the bias in the AI system stems from training data. And a really interesting research question now is how can and how should we regulate these training data sets? The Commission, the EU Commission, in its white paper that was published in February 2020 on AI, hints at this and suggests that we might need some novel rules. I just published a paper on this if you're interested in this context to inquire a little further into how a legal framework for these kind of data sets may look like. Now, one question, and I finish with this, remains, namely these fairness interventions that we just saw, for example, on the LSAT data set, are they legal at all? And here I just want to point you to two severe difficulties. One is in data protection law, namely the GDPR contains a prohibition to use sensitive data. In some protected categories, in fact, many of them constitute sensitive data, such as ethnic origin or religion. So it might be difficult to know about group membership in the first place. There are some ways to deal with this, I believe, under the GDPR. I have some theories on this. Maybe if you're interested, we can highlight this in the discussion. I just want to flag this problem here. And second, in anti-discrimination law, the enforcement of group fairness metrics might be perceived as affirmative action. That's called positive action in EU law, and the problem is that there are significant limitations on using affirmative action procedures, particularly in employment law. So there's certain CJU jurisprudence on this. I can't go into the details. Again, if you're interested, maybe we can take this up in the discussion. But as a main upshot, I would say that oftentimes, to satisfy the constraints of the law, we will need some kind of human intervention. It will not be possible to just automatically, in all cases, re-rank the candidates, but we'll have to look specifically at cases of specific legal interest, such as, for example, when there is a candidate with specific hardship that is supposed to be downranked, then we need to, feed this through another feedback loop and further objective assessment. But maybe that's not too bad, because I believe that in general, going forward, we will have to see much more of this human-machine teaming of precisely the kind of advice and interactive formats that Nina talked about in her previous talk. So with this, let me just briefly wrap up by saying that there is an abundance of fairness metrics in computer science. Our model tried to take two of these and bridge the divide between individual and group fairness measures, while at the same time minimizing information loss for the decision maker by using optimal transport theory. And that means that under certain fairness constraints and under certain assumptions, we can guarantee decision maker utility maximization because we minimize the information loss. Third, in the concrete deployment, there are a lot of normative decisions that have to be taken, really serious normative decisions about how to choose this theta value or what fairness metric to choose in the first place. And there are also, and we shouldn't forget this, legal constraints on algorithmic affirmative action that actually render the concrete deployment of fairness interventions difficult in some contexts. So the upshot is that yes, we may use technical tools to remedy bias. I think that's one of the big advantages of AI systems over human decision making, that we can choose consciously certain decision making parameters, but we need a robust normative framework to make this work in a legally compliant and ethically sound way. Many thanks with this for your attention, and I'm really looking forward to the discussion.